Welcome to the topic of basic visualization technique and the pair view. So in this lecture, I'm going to talk about a few common visualization techniques that you can use to look at your data. I will give you the basic idea how those techniques are doing for you. And in the end of this video, I have a quick demo of pair view that can produce some of the visualizations here. So the topic of interest include mesh view, outer surface with attributes, slicing. You can place glyphs at your grid points. You can do ISO contouring. You can also perform some more advanced visualization operation called volume rendering. I'm going to give you a live demo to show you how to generate some of the common visualizations using a software called pair view. So what is a pair view? Pair view is an open source application that's been used widely to visualize large-scale scientific data sets. It can run on a variety of different platforms. For example, your laptop. It can also run on big supercomputer. Pair view is developed using VTK, the visualization toolkit. But unlike VTK, which is a library that requires the user to write C++, Python, or TK program, pair view provides an intuitive graphical user interface that allows the user to easily look at data without any programming. It has very modular design, which means it can be easily extended. In fact, if you want, you can write a Python script to add additional features to pair view. Finally, pair view can be run on big supercomputers. That computers may have hundreds of thousands of cores, and it will be able to scale to a very large data set. This is just a very brief view of pair view software stack. At the bottom of pair view, there are several fundamental libraries. For example, OpenGL, which is used to perform graphical rendering. MPI, that is massively passing. This is a library commonly used for parallel programming. Because pair view can perform parallel rendering, it relies on a library called IST to combine many small partial images together into a final complete image. On top of those fundamental libraries, there is a VTK. So VTK, later we are going to cover some detail VTK, but basically VTK is a software library. It implements many different visualization algorithms. VTK is a library that requires you to write programs in order to produce visualization. Pair view built on top of the VTK, then it provides a intuitive graphical interface so that common user can look at the data much more easily. Pair view is not just a front-end program. It can be run on back-end powerful server. So you can have a laptop that run pair view client, and it will connect to pair view server running at the back-end, and you can do something more powerful. And pair view use Qt and also Python to generate user interface. Finally, the front end. Pair view has many different components, such as the common software, we call that pair view, which is a client program. It has PV-Python that allows you to write Python script to process data and add additional features. Also, it has Parallel Web, which is a web interface. Catalyst, which is a in situ component that can be combined with pair view. In situ means you run visualization with your simulation code. Because pair view is a general purpose visualization software, it can be used to look at many different types of data. Examples here are rectilinear, uniform or non-uniform, curvilinear, and unstructured grid or polygons. In our earlier lecture, we have talked about the data model for these different types of data. This is the pair view interface. It has many bar. Because pair view has many different visualization algorithms, so it has toolbars, so allow you to select different visualization techniques. ParaView is built on top of the concept called visualization pipeline. Essentially, it allows you to connect many algorithms together to form a processing pipeline, and then the data is going to go through the pipeline and being processed by different small algorithms before the final image is being produced. You can control the behavior of those algorithms using property panel. There are some advanced toggle tools, and finally, there's a 3D graphical view of the visualization. Okay, now let's look at what are some of the basic visualization techniques. The first one I want to talk about is the mesh view, which is a very simple visualization of your data. So basically what it does is to look at the mesh structure, convert the outer surface of each cell into polygons, and you just render the polygons. You can overlay the polygons with mesh line so you have a better understanding of the cell structure. So you can draw the mesh in either wireframe or surface mode using your preferred graphics library, such as OpenGL. I'm going to give you a demo using ParaView later. Of course, a lot of time we want to look at the attribute, not just the mesh. This can be done by map the numerical value at the vertices through a color lookup table, and then you assign color to each vertex of your polygon. And the color across the surface is basically interpolated using glow shading or other preferred shading algorithms, and this is done by graphics libraries such as OpenGL. If you only look at the mesh, you can only see the outer layer of your model, but a lot of time you are interested in the internal portion of your data. So how do you do this? To do this, you can perform something we call slicing. Basically, you intersect the mesh, the three-dimensional mesh, with a slicing surface. The slicing surface can be arbitrary shape, but in most cases, people use slicing plane. Assuming your slicer is a plane, you can represent the plane by a simple linear equation. And then you calculate the intersection point between the slicing plane and your mesh. And at the intersection point, you interpolate the data value and assign color. And finally, you display the resulting plane. Now, sometimes we want to assign graphical object to represent the data value at each grid point, and this is called glyphing. One example is that you can draw arrows at each grid point to depict a vector direction. This is very commonly used for vector field visualization. So here in the example below, at every grid point, you define a direction, and now you just draw arrow plot. But of course, this glyphing is used mostly for small data set because when you draw too many graphical icons, the occlusion is going to prevent you from having a good understanding of the data. So what else can we do? Now we can do something a little bit more complicated, such as contouring. So what is contouring? You want to display all the points in the domain that have a constant value equal to C. If your model is a 2D surface, then the constant value point is going to form a curve. We call it isocontour. If your data is defined in three-dimensional volume, then the points are going to form surfaces. So this is typically called isosurfaces. So later in this course, we are going to talk about some discrete algorithms that you can use to compute the isosurfaces. One famous example is margin cubes. The results are something you commonly see, that you have a different contour, different bands. Each band represent a constant values. Now this can be applied to 2D or 3D data. And this image below just show one example of how can you create discrete surface patches in 3-dimensional data. We are going to talk about this algorithm in detail. Finally, if you want to look at the whole data altogether, one popular technique is called volume rendering. This is basically a method that allows one to visualize the entire 3D data by simulating how the light is being transported through the volume space. Another way to look at it is you treat every data point as an element. You perform a 2D projection to the screen. And this projection is done by sending many view rays from the camera through space, and then you composite, that is, you combine the color together to form a final images. This volume rendering algorithm we are going to talk about in detail later in this course. Okay, now I have given an overview of basic visualization techniques. Now let's look at how we can use ParaView to generate some of the visualizations that I just mentioned.